All right, so we're going to start today just again, we're going to review a little bit more with these polyatomic ions and kind of the nomenclature structure piece that we were working on Tuesday. And so once again, it comes down to this is a recognition kind of thing. So how do we recognize that we have a polyatomic ion? Well, again, it's usually in that ending. If the ending is ATE or ITE, we know that we're dealing with a polyatomic ion. And if it's a polyatomic ion, then we need to consult our polyatomic ion page here to figure out what the formula is and what the charge is for that ion. So in this particular case, we were looking at phosphate. Phosphate is PO4 -3. So phosphate has that formula with that charge. Sodium, we should know already. Sodium is an alkali metal, group 1. It has 1 valence electron. It forms a +1 charge. So that's the charge that we're dealing with. Since the charges do not match, then we're going to crisscross to figure out the subscripts. And so we end up with the formula sodium phosphate is Na3PO4. So again, from a naming perspective, the naming structure with polyatomic ions is exactly the same as the naming structure was just for ionic compounds. We name the positive ion first, we name the negative ion second. Positive ion's usually metallic. The negative ion is either non-metallic or polyatomic. And so this table here gives us a list of compounds that involve polyatomic ions and some of the common uses for them. Don't really need to get too deep into this part of it. These are just kind of common example things. All right, let's look at some more examples. All right, aluminum nitrate. Now, from our study, we know that aluminum is Al+3, and we know that because aluminum is in group 3, all of the group 3, group 13, all the group 13, 3A elements all make +3 ions. Nitrate, we'd have to go back to the list, but nitrate is NO3 -1. So the charges do not match. So we've got to crisscross them out. I'm going to end up with AlNO3 taken 3 times. And so the thing that we want to avoid, obviously number 1's not correct because it doesn't balance the charges. Number 2's not correct because we've got the wrong ion here in the middle. We need NO3, not NO. There is a difference between them. So NO3 has to be the ion. And again, if we're dealing with polyatomic ions and we need more than one of them, we put that polyatomic ion in parentheses so that we can say that it's the whole unit. It's that whole cluster that is being multiplied, not just a part of it. right, any questions with that first one? All right, let's look at the second one. We've got copper 2 nitrate. So again, we have nitrate. We know nitrate is NO3 -1. What does the 2 in copper 2 indicate? Sean? Okay. It means that it has a charge of +2. Yes. Okay. This is real important to get into your head, because I'll tell you the most common mistake, and I'm talking about across the board, not just with you guys, not just with other students who are in introductory chemistry. I'm talking about my chem majors. When we first get into nomenclature, they love taking that Roman numeral and turning it into a subscript like that and saying, oh, the 2 means that there are 2 coppers. No, it doesn't. The 2 means that we have a +2 charge. And so if we have a +2 charge, we can see that we're going to end up with CuNO3 2 as the compound formula. And not this one over here. So the important thing to remember, the Roman numerals give us charges. They don't give us the formula. The Roman numeral isn't a shortcut to the formula. It's a shortcut to the charge. Okay, let's look at iron 3 hydroxide. Again, iron 3, we're talking about the 3 positive form of the iron ion. Hydroxide is a polyatomic ion. Its formula is OH minus. And so if we crisscross the charges, we get FeOH taken 3 times. That's this third one. With tin 4 hydroxide, tin is SN. 4 indicates a 4 positive charge. Hydroxide we just talked about is OH minus. If we crisscross the charges, we get SNOH 4 times. Yes. No, because it wasn't given in these examples, but let's just say, for example, let's add a 5th one here. Tin 4 oxide. We've got SN plus 4 and O negative 2. If I crisscross those, I would get SN2O4, which would be incorrect. The reason it's incorrect is because chemical formulas of ionic compounds always reduce down to kind of lowest terms. So since each of these subscripts is divisible by 2.
But yes, but the answer is no, because
it could be simplified, yes.
Okay, so you can, as long as you can simplify it.
Yeah, you can always cross them and then simplify, which is why if it's the same kind of logic for if I had a +3 and a -3, I wouldn't crisscross them because the charges match. But if I did, and I came up with SN3O3, I would just reduce that down to SNO. So yes, generally speaking, we can crisscross. But if the result is reducible, then we need to reduce it. If that's a better rule of thumb for you, then that's kind of what we're doing. All right, other questions here? All right, let's go the other direction then. Naming these compounds. So for the naming of these, remember, we've got to reverse it to figure out what the ions are, and then we just name the two ions to get the name of the compound. So if I reverse this, I have calcium plus 2 and NO3 negative 1. So what's the name of this ion, Ca plus 2? Just be calcium. Why don't we call it calcium 2? It doesn't have multiple charges. It has only the one charge, the charge that we dictate by the periodic table. So the Roman numerals there are only there if we have multiple possibilities. Calcium doesn't have multiple possibilities. It's only positive 2. Because it's not a transition metal. That's right. So NO3, we would need to go back and look at. NO3 negative 1 is the nitrate ion. So the name of this compound would be calcium nitrate. All right. For letter B, it's a little bit more complicated. One thing another way that we can approach these, since we have the sheet, is we can just kind of go searching for the value. So phosphate, if I go up to phosphorus, I'm going to see that phosphate here is PO4 negative 3. So PO4 is the ion that we saw in the compound. So we know it's phosphate. And we know it was PO4 negative 3. What is Fe? Right, it's iron. What is its charge? In this case, it would be 3. Why do we know it's 3? Well, we've got to look at the ratio. I've got 3 negative. It has to be matched by 3 positive. And since there's only the one iron there, the iron must be 3 positive to match it up. So I need to put this as iron 3 phosphate. Again, why the Roman numeral? Phosphate's a transition metal. And with the exceptions of just a few transition metals, cadmium, palladium, and silver, all of them get a Roman numeral except for those 3. So if it's in the middle of the table, you're putting a Roman numeral on it unless it's one of those 3 exceptions. All right, questions with either of these 2? All right, let's do some more then. So once again, I think it's the way to kind of approach this is let's look for these clusters on that table and see if we can't figure out what the names are, and then we can work backwards off of that. So our first one was SO3. SO3 has a -2 charge. It's called sulfite. So this is SO3 -2. Mg is magnesium. Magnesium is in group 2A. It only has the +2 charge on it. So now we just put those together. Magnesium sulfite. If we go back to the chart, SO4 is sulfate. It also has a -2 charge. So this would be magnesium sulfate. For the last one here, we're looking for PO3. PO3 is down here at the bottom. It's phosphite. It also has a -3 charge, which might be important to us. We're also dealing with, this is a lead. Pb is lead. Now, where do we get the charge for the lead? Because lead is a transition metal as well. Yeah, here's where going backwards on that crisscross, we can figure out that's lead too. So I'm not making you memorize the polyatomic ions, and that's definitely a good thing for you because there's a lot of them. They're very varied. But if we're looking for some trends, some things that we can kind of latch onto just to make our lives a little bit easier. One thing that you should notice is that the difference between an 8 and an ite is 1 oxygen. So if I was going to guess what phosphate is, I would just add 1 more oxygen. It'd be PO4 -3. So there are some patterns in there that if you work with this enough, you can start to recognize, and it does help. But again, I'm not asking you to memorize that. So using the chart is more than okay in that circumstance. Alexis? So when we do the chapter 6 quiz, I will provide you a copy of it. For exam 2, I'll provide you a copy of it. But certainly for your homework, have your ebook listed out to that page, or find some other version of it online. There's dozens of them out there. Because it'll help a lot to have just that side-by-side reference as you're going through the homework. All right. All right, let's try this out here. So I want you to try to do these three on your own. I'm going to see if I can open a side by side and have the two next to each other here. That might be a little bit helpful. Right. Yeah, that's too much. Right. So find the polyatomic ion, try to match it up. Especially for those transition metals, you need to know the charge so you can figure out the Roman numeral that goes on the metal. See if it's the charge data. All right, so if you did it correctly, you should have been able to walk over to this side and find sulfate and kind of reversing our charges there, find out that we are dealing with iron 3 sulfate in this first example. In the second example, we're dealing with a phosphide ion here. This is barium phosphite. And again, barium is a main group element. It's on the part of the table that does not have flexibility in charge, so we don't need a Roman numeral. It's not a transition metal. Last one, you look at CO3 here, you should find carbonate. Carbonate has a -2 charge. That should have been your clue that the nickel had to be a +2, since there were no subscripts. So if you've got a compound that doesn't have subscripts, you got to pay special attention to what the charge is on the polyatomic ion, because that's going to tell you the charge on the metal as well. All right, any questions with those three? All right, take a breather. We are done with ionic compounds, at least for a while. Now, that being said, we have to completely switch gears to talk about molecular compounds. And when we get into molecular compounds, we have to understand that the whole vantage point has changed. We're not talking about one atom giving electrons to another atom. We're now talking about two atoms collectively sharing electrons and using that sharing to ultimately get itself to an octet, to fall into the octet rule. And so where we see this happening, and so these compounds that we are talking about, we call them molecular compounds because they are what make molecules, but we'll also hear them referred to as covalent compounds. And the reason we call them covalent compounds is because the bonding that exists inside of them are covalent bonds. Now, what does a covalent bond mean? Well, as you might expect, co means together or shared. Valent meaning valence electrons. We have valence electrons that are together between two atoms. This is the kind of stuff that happens in non-metals. So non-metals tend to behave this way. And to probably understand this kind of concept the best, we need to go back to what we were talking about on Monday and Tuesday with those Lewis dot diagrams and figuring out how many dots and how many of those dots are paired versus unpaired. So we take, for example, hydrogen. Now, if we look at the Lewis dot diagram of hydrogen, what we will see is that we've got a hydrogen with a single electron floating around about it. Now, that individual hydrogen atom's doing okay. Because it is so small, it's only one electron away from a noble gas configuration as well. Helium only has 2 electrons. It's one of the few exceptions to the octet rule. Helium doesn't need an octet because its energy level is so small, it can only hold 2 electrons anyway. So hydrogen's doing okay. But as we've seen with other things that are doing okay, they tend to want to be doing better. And so what we see in hydrogens is that if we have hydrogens together, those unpaired electrons will find each other and they will be shared covalently between the 2 hydrogens. And the net result is that instead of hydrogen atoms, we're going to make a hydrogen molecule. That hydrogen molecule is going to be held together by that covalent bond between the 2 hydrogen atoms. How do we show covalent bonds? Usually with lines. Sometimes we can show them also like this, where we can show that those two electrons that they're sharing are between and kind of holding it together. Now, why this happens has everything to do with attraction. Just like we saw in ionic molecules, where we have positive ions and negative ions and they attract each other. We have similar kinds of things happening in covalent molecules as well. The only difference is the attraction isn't positive to negative between ions. It's positive and negative between protons and electrons. Those attractions that occur as we get those two hydrogen atoms closer together, the nucleus of one atom starts to attract the electrons of another, and vice versa. And so eventually that attraction between nucleus and outer electrons of a different atom draw those atoms close enough together that they eventually can form a bond. When they form that bond, they release the extra energy that they are carrying to keep that electron separate, and we get a more stable molecule as a result. Like I mentioned with the previous example, we see this same kind of phenomenon in other molecules, and we can show that relationship that exists in kind of the same way. What we're looking for is, if we are looking at Lewis dot diagrams for individual atoms, we're going to start looking for unpaired electrons in those dot diagrams. And those unpaired electrons in those dot diagrams, those are the ones that are going to be shared. And so we can go from, in this case, fluorine, where we've got two atoms that are separated, to now we have two atoms that have electrons that are being shared between them. And we can either show it like this, where we can see that each fluorine now owns those two electrons between them, or we can show it with a line to indicate that that bond is there. Either way, each fluorine now can count among its electrons a total of 8. The 6 that it has in dots around it, plus the 2 that are being shared between the fluorines. That's how it gets to 8. And what I was trying to show there, either way is acceptable. Either way is acceptable. Now, if you're asked to do some molecule drawing in mastering, it's probably going to look for the lines. But we understand that those lines are just a representation of those electrons being shared. Now, this kind of self-bonding takes place in a very limited series of elements here on the periodic table. In particular, we talk about 7 diatomic elements. That is 7 elements: hydrogen, nitrogen, oxygen, and the halogens. Those 7 elements are the ones that form diatomic molecules naturally. Now, that's not to say that these are the only ones that bond with themselves. What we will find is that a lot of the nonmetals will self-bond. But these are the ones that do it the most simply. You know, if we look on, we talked briefly about carbon. Carbon forms, graphite sheets. It forms diamond structures. It forms nanotubes. sulfur tends to form 8-membered rings where each sulfur attaches itself to 2 other sulfurs. Phosphorus tends to make these weird little tetrahedral 4-cornered prisms. They all tend to do something. Most of them don't do nothing. It's very rare to find a non-metallic atomic sample unless we're talking about a noble gas. Now, how this often works is something that we were alluding to earlier this week. And it's the idea that if I'm looking at the Lewis dot diagram, of an element, I can look at a general kind of rule here. And I can count up the number of unpaired dots on each one of these elements and get an idea of how it usually bonds covalent. So we already talked about hydrogen. Hydrogen only makes 1 bond. Didn't talk about boron. Someone did ask about it. And I said, well, we'll just kind of get to that later. Well, boron doesn't technically obey the octet rule. It kind of obeys this dot pairing rule instead. But everybody else follows the octet rule and does the dot pairing. So if I'm looking at the carbon group, the nonmetals in the carbon group, which include the metalloids, silicon and germanium, they all behave in this kind of way. We've got 4 unpaired dots. They tend to make 4 covalent bonds. In the nitrogen group, nitrogen, phosphorus, arsenic, they tend to behave this way. They've got 5 valence electrons. So that means that they've got 2 paired and 3 unpaired. Those 3 unpaired dots tend to make covalent bonds. In the oxygen group, oxygen, sulfur, selenium, they all behave this way. 6 dots, which means they've got 2 pairs and 2 sets of unpairs. Those 2 unpaired electrons, those go out and make bonds. Could you? Yeah. So oxygen and sulfur could pair up that way. They usually don't. And that gets that's more of a factor of what sulfur is than what oxygen is. As you go down the periodic table, the bonding ability of those elements actually becomes greater because they become less and less attached to the octet rule. But in the first 2 rows of the periodic table, it's octet rule or nothing. And so their behavior is very, very predictable. And then with the halogens, group 7A, again, same thing. So we want to get into the actual drawing of these molecules here. And the easiest way to kind of go about it is really to play a very simple game of connect the dots. When we're trying to draw out molecules from elements, that's largely what we end up doing. We look for these unpaired electrons and we start matching them up to each other. And that becomes the basis of a chemical bond. So in the case of methane here, not only would we have this 1 hydrogen, we would have 3 others. and they would all just start pairing up. And that would become the basis for our molecule, which shows the carbon in the middle surrounded by all of those hydrogens and all of those shared electrons, which we could condense into this line structure just for a little bit more clarity, a little bit less confusion. So that's the main reason why we use the lines, just because it's a little less cluttered in its look. Here are some more examples of these kinds of molecules. And again, we can, we already did the drawing, the mock-up for methane here, but we could easily do the same kind of thing for ammonia. I've got nitrogen, I've got hydrogens, and I just really need to connect the dots to figure out the bonding structure. These two dots here on the top of the nitrogen don't get shared. They stay just with the nitrogen. Everybody else pairs up. We end up getting a molecule that looks like this. For the water, starting with oxygen and adding in the two hydrogens. I pair up the unpaired electrons of oxygen to a hydrogen. I end up getting two covalent bonds as a result. And that's my water molecule. Now, believe me, it does get more complicated than this, but we're going to largely stay away from the complicated examples. There are a couple of things that I'm going to show you just to kind of help us make sure that we're in the right frame of mind when we're doing these kinds of manipulations. First of all, it is possible to have multiple bonds between one atom and another atom. So if I have two unpaired dots on oxygen and two unpaired dots on another oxygen, I don't have to, okay, well, this one can only make one bond over here, so I got to make another bond to a different atom over here and something else crazy like that. They can match up in whatever configuration is needed. So if I have two oxygen atoms, both with two unpaired dots, those two unpaired dots can link up with each other to make what we call a double bond. That double bond has two sets of electrons in it. So two sets of electrons would be a total of 4 electrons. That double bond is sharing 4 electrons instead of just 2. As a result of that extra sharing, there's going to be extra attraction. That double bond is going to be stronger than a single bond, because you've got more sharing going on, which means you've got more attraction between the two atoms and each other. Triple bonds are also possible, where we've got 3 sets of electrons being shared between 2 atoms. So we see this a lot with nitrogen and phosphorus kinds of compounds, where we can get that triple bond to take place. In a triple bond, 3 electrons from the one atom, 3 electrons from the other. We're talking a total of 6 electrons being shared between the 2 atoms. Obviously, with those extra atoms or those extra electrons in the middle, we're talking about a stronger level of attraction. Triple bonds are even stronger than double bonds. Double bonds are stronger than single bonds. Okay, so when it comes to a process here, How do I draw a molecule? How do I draw carbon dioxide? The question here kind of breaks down into some parts. And so your book presents some of those parts here. We're going to even simplify what they say a little bit more than they do. So this first step is a good one. How do we arrange the atoms? Well, it doesn't say, it says, it's telling us that the center atom is carbon. How do we know that? Well, the reason we know it's carbon is if we go to that dot diagram, there's carbon. There's oxygen. There's another oxygen. Which one of those atoms has the greatest ability to bond? Which one has the most unpaired dots? The carbon. It's got 4 unpaired dots. That's how we know carbon is the center atom. We can get into a long discussion about a whole bunch of other things, but that's really what it comes down to. That carbon is the best suited to be in the middle because it has the greatest capacity to bond. It can make 4 bonds. The oxygen can only make 2. This second step here can be useful at times. It can be really useful when we're trying to double check, make sure that we drew the structure correctly. So how many valence electrons are we talking about? Well, we've got a carbon. Carbon has 4. Each of these oxygens have 6. 4 plus 6 is 10. 10 plus 6 is 16. So when we get to the end of the road here, we want to make sure that there are 16 electrons in the structure. If we don't have that, then we know we made a mistake somewhere. Here's where we kind of get off the reservation a little bit. I don't like these steps. I already told you that as far as we're concerned, bonding is a game of connect the dots. And it's no different here. We just got to know which dots to connect. Now that we've established that carbon is the center, well, let's just start connecting dots and see where that gets us. So I connect one carbon, I connect carbon to one oxygen, I connect carbon to the other oxygen. Okay, that's great. Is that all we can do? No. I can clearly see that each oxygen has 1 more dot that needs connected, and the carbon has 2 more dots that need connected. Well, let's go about doing that. There. There. Now we've connected all of our dots. Carbon has no dots that are not connected. Oxygen has no dots that are not connected. All that we need to do is just rearrange this, rewrite it so it looks a little bit prettier. So I'm going to put the oxygen here. I'm going to put 2 lines to represent the double bond to carbon. This oxygen has 4 more dots around it. I'm just going to kind of put those dots around. I'm going to do the exact same thing on the other side. There's my correct structure. It doesn't have to be this complicated. Now, again, we're presenting this from a simple kind of point of view. There are places where these steps make the most sense, but we're not going to use any examples where it does. Triple bonds, same kind of idea. I can see in the nitrogen that I have 3 unpaired dots. And so if I line them up and connect them, there's the basis for the triple bond between nitrogen and nitrogen. So as far as molecule drawing is concerned, that's as complicated as we need it to be. And if you go into your homework assignment, you're going to see that there are going to be a couple of examples where you're going to have to draw molecules. But I selected examples that were in this kind of simpler variety, where we didn't have to go into more of that kind of rigorous counting and recounting and, you know, shifting lone pairs down into bonds kind of thing. It just doesn't work. It doesn't make sense. Let's take a look at naming. Now, what I want you to recognize about naming molecular compounds is that structurally speaking, the naming system for molecular compounds is very similar to the naming structure for ionic compounds. We're going to name them in order. So we've got an element that's first. It's going to be the first element that we name. We've got an element that's second. It's going to be the second element that we name. The second element, get this, is going to have its ending changed to IDE. That sounds familiar, but that's because that was most of what we did with most of them on Tuesday. The only real difference is a couple of things. One, subscripts are going to get turned into prefixes. Since we don't have charges to fall back on, we're going to use a series of prefixes to tell us how many of a given atom there are. I'll show you what the prefixes are here in just a second. The second thing is just really a pronunciation thing. If the results of putting that IDE on the end or smashing a prefix on the front ends up giving us a weird combination of vowels, we're just going to omit the first vowel. Yeah, we're going to take it away. So, you know, for example, if there are 4 oxygens, the prefix for 4 is tetra. Oxygen would be either oxygen or oxide. Well, instead of saying tetraoxygen or tetraoxide, I'm just going to take that A out. Tetraoxygen, tetroxide. It's a stylistic thing. Basically, so you don't have to make your mouth make a bunch of weird vowel sounds in a row. Huh? Well, they've got other reasons for that. Okay, here's some common molecular compounds. You know, we'll get into these a little bit deeper. Interesting. Okay, I thought I had a prefix slide in here. It turns out I don't. So let's make one. All right. So if I have one of something, it's going to fall into one of two categories. If it's the first atom in the molecule, it's not going to have a prefix at all. We'll assume that the one is implied there. If we're dealing with the second atom, the prefix for the number one is mono. For two, the prefix is di. For three, the prefix is tetra, it's tri. For four, it's tetra. For five, it's penta. Six, hexa. And so what you should start to notice once we get into these is that it falls into kind of your standard geometry prefixes. With one little exception, and it's number 7. 7 is hepta instead of septa. But otherwise, 8, octa, 9, nona, and 10, deca. So again, the structure here falls into, we name the first element, we name the second element. We add prefixes to the beginning of each element based upon what the subscripts are. And so with that in mind, if we look at an example like this, then we can start to break it down into its pieces. N, we know, is nitrogen. Cl, we know, is chlorine. Since there is only one nitrogen, we don't need to add a prefix to it, so it is just going to stay nitrogen. Since there are 3 chlorines here, we're going to need to add the prefix tri, and we are going to change the ending to IDE. So that means the name of this compound is going to end up being nitrogen trichloride. 1 nitrogen, 3 chlorines, 1 molecule. This will take some getting used to, especially after hammering ionic compounds for the past several days. But it will get easier with practice. All right, let's do one last example. We'll call it a week from here. And obviously we didn't get through all of this. That's okay. We'll pick up where we left off on Tuesday. I'll shove everything back accordingly. So post lecture will be due Tuesday night. The end of chapter module will be due on Wednesday night. And we'll see where everything out of chapter 11 falls out from there in terms of when we do the quiz and all of that other stuff. So the first post lecture assignment ends with the polyatomic ions. So I split it basically into ionic and covalent. Those are the 2 post lectures. All right, so this first one, we've got silicon, we've got chlorine. The prefix here is tetra for 4. So silicon tetrachloride is the correct answer. For the second one, we're going to have 2 prefixes. we're going to have di for the phosphorus and penta for the oxygen. So that's where this one's going to come in, diphosphorus pentoxide. Again, penta oxide, we've got that double vowel thing going there. We drop the first vowel. So that's why it's pentoxide instead of pentaoxide. Again, we've got double prefixes here. So di and hepta for 7. So dichlorine heptoxide, option number 1 is correct. And again, it's the same thing. Hepta oxide, we've got 2 vowel sounds there. So we drop the first one. Heptoxide ends up being the result. So again, we will pick up with this. We'll do more of this stuff. We'll get into the last bars of chapter 6 on Tuesday. But for right now, other than the assignment that's due this evening, I want you to put chapter 6 away until we get back to Tuesday. And you can start working on that kind of stuff then. Until then, get ready for the exam on Monday. Hopefully I'll see you tomorrow at the study session. If not, I'll see you at the exam. Have a good day.